Welcome to this event. My name is Massimiliano Vasile. I'm the coordinator of the Stardust network, and this event is a sort of overview of what Stardust has done in these 4 years. And we have here a number of speakers and guests who are going to either explain what the problem is with asteroids and space debris, or provide some of the solutions that the Stardust network developed in these years. So first of all, what is Stardust? Stardust is a research and training network that started about 4 years ago, supported by the European Commission, to study two problems. One, how to protect our planet from an impact with an asteroid, and the other problem is how to protect our space assets from a collision with space debris. At the beginning, we were 14 institutions, including the European Space Agency, but during these 4 years, the network increased in size, and we are now 18 partners across Europe. You see, we are covering pretty much every part of Europe, and we have a mix of universities, research centers, and companies. Essentially, most of the major actors in Europe that are dealing with asteroids and space debris. But as part of our activities, we also collected collaborations from across the world, and we have now collaborations with the University of Arizona, with JPL, the University of Kyoto, and also the University of New South Wales. What was the idea of the network? The idea of the network is that you have two communities, one that is dealing with asteroids and one that is dealing with space debris. And essentially, they have to do similar things. So they have to observe the sky, they have to determine the orbit of these objects, and then they have to predict a possible impact, and then they have to do something about it. And in some cases, you want to dispose of space debris, or you want just to deflect an asteroid. In other cases, you might want to reuse or exploit, basically, these objects. So in terms of research and what can be done, the two communities had a lot of things to share, and a lot of techniques could be shared, but also one could try to scale one technique to solve both problems. So some of the highlights of this network, but you will see more in a minute. So we managed to study the chaotic motion, for example, around the Earth, to see if we could exploit basically resonances to study the evolution of the space environment and of debris, and maybe get rid of debris using this idea. We developed technology, innovative technology, to detumble space debris, for example, using eddy current, and you will hear something about this. And also new methods to deal with the propagation of uncertainty, and this is very important when you do re-entry, so we had to develop tools to study the demise of these objects and check the probability of casualties on ground, but also the probability of casualties if an asteroid was impacting with the Earth. So many different types of innovative techniques, and Stardust had the luxury to study all these techniques without the need to have an application on the near term. So we could experiment with new ideas. So today we have many distinguished guests with us that are going to, as I said, explain more about asteroids and space debris, and also some people from the network who are going to tell you more about what we did. So here with us we have Professor Daniel Shears from the University of Colorado, who has been involved pretty much in every single asteroid mission so far. who's going to tell us more about proximity operations, and then we will have Cheryl Reed from APL, who's involved in the AIDA mission and will tell us more about AIDA. After that, you will hear something about space debris from Christophe Bonal from CNES and what we need to do in terms of technology. And then Dr. Francesco Toputo from Dinamica, one of the members of the network, will show you some of the technologies that we developed within the network. After that, you will hear again from CNES some of the open problems that we have in tracking, basically, space debris. And Professor Giovanni, the person from CNES is Juan Carlos Duado Perez, who is the head of the Space Debris Modeling and Risk Assessment Office. And after that, Professor Giovanni Gronchi from PISA will tell us something about how to determine the orbit of these objects. And then at the end of this session will be on the future. Okay? And we will have something from the University of Arizona. They have a center that is looking at the future of space debris and the space environment. And we will see how what they do in the US and what we propose to do in Europe can solve some of the open problems. Okay, so we have now Professor Shears, who is going to tell us something about how to navigate near an asteroid.
So thank you very much for the introduction, and it's very much an honor to be here to tell you a little bit about asteroid exploration and what has happened, what is happening now, and what we hope to do in the future. So I just have a few slides, and first thing I want to point out is what the past exploration of asteroids has been. And going back a few decades, much of this really consisted of flybys of asteroids, where the spacecraft would very rapidly fly by the asteroid and take a picture of it, maybe measure its mass, but there's not much more that you could learn about the body. You only see one pose of the asteroid, and you don't get to understand the full system, if you will. About 15 years ago, the NEAR mission, the NASA NEAR mission, went to the asteroid Eros and actually went into orbit around it, eventually landing on its surface, and that was the first close-up view we had of these asteroids. Subsequently, about less than 10 years ago, or 10 years ago or so, the Hayabusa mission from Japan went to the asteroid Itokawa and carried out a long period of not orbiting around this body, but hovering about the body, never going into a full orbit, always using its thrusters to keep its distance from the asteroid. And eventually they were able to collect a sample from the surface and bring it back to Earth a few years later. So this is the sort of the history, or the old history, of asteroid exploration. Currently, as you know, there's a lot of activity going on with asteroid exploration and small body exploration as well. Very exciting was the Rosetta mission, which as of this morning is now over. I don't know if you were here this morning at 5:30 to see the final landing, but it was very exciting, although bittersweet too, because it was such a beautiful mission. It's very sad to see it end in some ways. In this mission, they had to contend with strong outgassing from the comet, yet they mixed together orbits around the body and flybys of the body. The Hayabusa 2 mission is currently en route to its target asteroid Ryugu, where it will carry out very similar operations to the Hayabusa mission at asteroid Itokawa. And here we have a comparison of the sizes of these two. This new target is actually much larger, and they have several very innovative approaches to investigating the asteroid, including an impactor which will hit the surface of the asteroid and create a crater, which will allow them to see inside the subsurface of the asteroid. Another exciting current mission is the OSIRIS-REx mission to the asteroid Bennu. This just launched not even a month ago and is now on the way to the asteroid. Here we will also carry out some innovative orbital dynamics around the body in order to understand and measure the body, and ultimately we will come down to the surface and take a sample and bring that home as well. So that's sort of the current activities in asteroid exploration. And there's many future challenges and future things that we wish to do in this area. One of which is to develop spacecraft formations at small bodies, which can orbit around these bodies in a very synchronized way and keep their distance from each other and carry out stereo measurements or differential gravitational measurements of this environment. That is a very innovative and exciting possibility that we hope to develop in the future. Another one is to develop and understand better how we can explore the surfaces of these asteroids. And these are some simulations of surface rovers landing and bouncing across an asteroid surface, and surface interactions here for the OSIRIS-REx sampling device as it interacts with the asteroid surface, which is in a microgravity environment. Another key area of development is the autonomous guidance and control of spacecraft around asteroids, where we may not have to send all the commands from the Earth that the spacecraft will carry out, but instead we can rely on artificial intelligence like algorithms in order to determine what to do at the body. So this is my brief introduction to asteroid exploration, and I must apologize that I now have to leave and catch a taxi to the airport so I can make my flight, but I thank the organizer for being very accommodating for me for this.
Okay, thank you very much. Do you have time for one question, maybe?
If there are, but
since Professor Shia has to run to the airport, if you have a question about this. One question. Yep.
Can you start apart from the asteroid with a rover, with a arm? What kind of thing do you use to extract pieces?
So the question is, what sort of tools, what sort of devices do we use to extract pieces from the asteroid? And for the OSIRIS-REx mission, we actually used compressed gas to move the surface covering, the regolith, into captured areas. And so we blow the regolith into a sack, essentially, that we then capture all the regolith and bring it home. The Hayabusa mission instead uses a device where they put a cone on the surface and they shoot a bullet in the surface and they collect the debris from that into a sample chamber and bring it home. A future mission, such as NASA's ARM mission, actually wants to have grappling arms that will come up and seize a boulder on the surface and actually extract it from the surface and then bring that back to a lunar stable orbit. Yeah.
Okay, thank you very much.
Okay.
Thank you very much. We can move to the second speaker, who is going to tell us more about how to deflect asteroids, and in particular what the AIDA mission is planning to do.
All right, good morning. I'm Cheryl Reed. I'm the project manager for a mission on the U.S. side, DART, under a collaboration with ESA called AIDA, and the ESA spacecraft is called AIM, which I'll talk a little bit about both today. So this is another regime of research in the area of asteroid and comet planetary defense. And what I show you here is the regime of potential mitigations that we are studying for asteroids that are deemed potentially hazardous to the Earth. So statistically, most of the potentially hazardous asteroids fall into this realm, where you see right here, which is above the size of 140 meters. And so the predominant mitigation technique for this size of asteroid is a kinetic impactor. DART, which is our impactor spacecraft, is within that regime relative to the target that we have chosen, which is the Didymos binary system. For comparison, the mission Deep Impact target is up in this regime, and that target was on order of 7 kilometers. So when we talk below this level, we are only in a position today to likely be able to do what we call a civil defense response of warning potentially, as opposed to actually attempting to remove the incoming object. Next slide. Let's see. Okay. This is an overview of the mission itself. The mission is scheduled, it's getting ready to go into Phase B. And you can see here the target system that IATA is going for is a binary system for which we have never explored. This would be a first to go to this type of system. And the DART spacecraft would perform the kinetic impact with the satellite of that system, which we refer to as a nickname of a Didymoon. So Didymoon is about 160 meters. The primary is about 800 meters. The orbital period of Didymoon is about 12 hours, and we predict that we will deflect the orbit period of Didymoon by about 7 minutes. We will be able to see from the ground, from optical and radar, we will actually be able to measure the deflection in that regard. AIM is the ESA spacecraft, which is an observatory not only to do the scientific analysis associated with the mission, but also to demonstrate many different types of technologies. AIM would be on station before the impact. Let's try this again. During and post. So this last chart shows the complete IATA scenario together, focusing on the AIM pieces. You can see that they launch before us. They get there before us. They do pre-characterization of the asteroid system before we actually perturb its state. They're going to do some technological experiments with CubeSats and a small lander, much like the mascot lander that is flying on Hayabusa 2. They continue the characterization, do other types of optical comm and interplanetary satellite experiments. They are then there for the impact, and they are then will do characterization post-impact. And some of these experiments will also put artificial craters, if you will, on the surface of the body, so that we can compare the crater that will be made by the kinetic impactor as well as the ones that are made by the experiment itself. And with this comes some very rich science for also understanding all of the physical properties, the dynamics of the system, and the interior structure as a first visit to a binary system. So this would be the first demonstration of a kinetic impactor, and one of the leave behinds is to refine all the models that are out there to be used for predictions of these types of events. Thank you.
Thank you very much. Thank you very much. Do you have one question? Because again, we have the same problem with the airport, I think. You will probably need to leave very soon. So no? Okay, so you saw two interesting presentations on exploring asteroids and also how to try to deflect asteroids. And what I'm going to show you now is a few examples of what we did within Stardust to address some of these problems. So you heard that the future is to have a formation flying around an asteroid. And in fact, one thing that we did within Stardust was to study autonomous formations in the proximity of asteroids. So we studied two different problems. One is how you have multiple spacecraft coordinating their motion around an asteroid, and also how to approach an asteroid with more than one spacecraft and improve the ephemeris, so your knowledge of the ephemeris of the asteroid. And in fact, what we managed to do was to show that you see here the position and the velocity of the formation with 4 objects that are flying close to an asteroid. And we are able to maintain the formation autonomously just using cameras and LiDARs with interlink communication, even in the case we have failures on board. So if we start having some instruments that are failing, and it's very important when you have an autonomous mission to be able to still control the formation. At the same time, we managed basically to go from several thousand kilometers of uncertainty in the ephemeris of the asteroid down to less than 100 meters of uncertainty, thanks to this coordinated orbit determination with the formation of the satellites. But we also try to change the orbit of Didymoon, not with an impactor, but we use a more exotic approach. We use a single spacecraft placed in a control equilibrium point in the gravity field of this binary system, and shooting with the laser at Didymoon and extracting material from Didymoon. And this way you can analyze the material, but you also change the period of the moon. This is work that I did with one of my PhD students who is here in the room, Nicholas Thierry. And we managed to show that within the time frame in which AIM is orbiting Didymos, with a reasonable size in terms of power, optical power of the laser, so something that you can actually install on board, we can achieve the same level of change of the orbital period of the moon. Of course, in terms of technology, it is more challenging, but Stardust is thinking of the future. And we look also at the deflection in a slightly different way, not looking at the mass of the object and the time we have, but the orbit of the object. So if we take the distribution of asteroids that we know, and we put this on a graph in which you have the same major axis and the eccentricity, and you try different techniques, so the kinetic impactor, the laser, or the ion beam shepherd that is blowing ions to push the asteroid, you can basically map where one method is better than the other. And you realize that the kinetic impactor is very good when you have deep crosses. So when you have a high eccentricity, for example, so you have a steep intersection with the Earth. But you want to use different techniques, like a laser or a low thrust push, if you have a shallow crosser. So when you have a low eccentricity and you are closer to the Earth. So this is the kind of approach that we take, and we can build a map that is slightly different from the one that you saw before. Do you have any question on asteroids? If not, we move to space debris.
Okay, thank you very much, Massimiliano. It's, there was a question. Please, this fourth row left.
Are this flight like we're surveying the skies for this asteroid? Yeah, so all these like prevention systems and everything depends on surveying the skies for the asteroids themselves. But well, the statistics say like it's how probable is that asteroid that we are not we don't know about just appears without much time to prepare. How do you handle that cases?
those cases. You cannot use a gravitational tractor. You cannot use many
That's a question for you.
ways.
Okay, it is true that we don't know about all the asteroids that are out there, and but we continue to find them every day with the ground-based systems. And actually, in the NASA Discovery competition right now is a mission called NEOCAM, which would be a space-based mission that would find even more. But a lot of it depends on the size as to when we can actually see them, and also relative to the sun. If you use the Chelyabinsk example, they were too small, and we were quite surprised in that regard. And of course, they didn't hit the surface, they exploded. Those are estimated to be something at about a 20-meter size. So it's still a very difficult problem. We find more and more every day, and with the current systems that we have, it'll still take anywhere to a decade to find probably 90% of the population, but we're still looking.
Thank you.
Okay, thank you very much. We can move now to the next speaker, Christophe Bonal from CNES.
Okay, so thank you very much, Massimiliano. It's a very good idea to merge the two communities like this, and it's plenty of synergies. So I'd like just to flip through 5 pages just to give a global overview of the question of debris. So the first one is clear, the mass of debris in orbit, and their number is steadily increasing since 1957. Okay, the curves are quite clear. Okay, and this despite mitigation measures which are started to be adopted in '95, and despite a drastic reduction in number of launches compared to the years of the Cold War. What do we fear about them? First of all, random re-entry. Okay, you should know that there is one large object, one large satellite or stage, which re-enters every week, and even a little bit more. Here is a nice picture of the Falcon 9 debris, which fell in an Indonesia village a couple of days ago, so just before the conference. Unfortunately, they have 20 to 30% survivability in terms of mass, so which means that it can drive some risk of casualty. Second feared event is small debris impact. So it's a spread to operational debris, operational satellites, typically in the zone of these 2 to 5 millimeter are dangerous enough, so due to their kinetic energy, to kill a satellite or to wound it, let's say. There are plenty of unexplained failures every year. Here is a nice image of the hit that occurred on the 23rd of August on Sentinel-1A, documented by Dr. Krag here. The third feared event is the large debris impact, so that's a different thing. It's a collision, hopefully very seldom, collision between large objects, and which regenerate thousands of new catalog debris. So the frequency is hard to know because these are very rare events, one every 5 years, one every 10 years. But what we know is that they generate some kind of typically 2,000 new objects, and so on and so on. So with this, we fear a potential Kessler syndrome, which is a kind of cascading effect, uncontrolled increase in the number of debris in orbit. So what can we do to avoid this? So be clean. So for this, we need really mitigation rules. The highest level of mitigation rule is very clear. It's that long-term, have clean operations, no debris left. It's really the American national parks motto. Everything that goes in shall go out. Okay. Well, today we're not able to do so yet, technology-wise and commercially-wise. So what we need is to apply the current or medium-term rules, which are very simple, very logical, be clean, so no operations, debris such as clam bands, shrouds, bolts. Saying no voluntary fragmentations. It appears a little bit funny, but you should know that there has been more than 50 voluntary fragmentations in space, which have generated thousands of long-lived debris. No accidental fragmentation, so for this we need to passivate systematically. We need to to protect the most critical, valuable areas. So these are 25-year rule in both low Earth orbit and GEO. Collision avoidance, this is very, very important. Unfortunately, we cannot always do this. And be careful of casualties and ground. So for this, we define some kind of limitation to with an allowable threshold. Okay. Good news is that we have very good coherence at worldwide level, because we've been working on this now for more than 20 years, so everyone shares the same rules based on the IAC guidelines, which were adopted in 2002, which were declined then into the ISO 24113, and I sincerely hope that one day this ISO will be systematically applied in whatever contract we pass, then we have national laws, guidelines, and so on. But this may not be enough, and so today we don't know if there is enough. We must be very careful. Today there is no clear demonstration that we need active debris removal, and all the calculations are still going within the world. But if we need it, if it is necessary, then there are plenty of possibilities. And so the few challenging points are described here. First of all, technically, yes, we're using lasers, we're using navigation and things like this, so plenty of techniques which are very similar to the ones that we're using to avoid asteroids. So I would say, but it's a little bit fast, I would say techniques is not the problem. The problem then is, of course, the financial hurdles. How do you finance this, and what are the business plan? Maybe we need a global program at the UN or IDC level. There are plenty of legal aspects. Are you allowed to go and fetch an object which is not yours? And even, are you allowed to go and fetch an object which is yours? Even this is not obvious. Plenty of insurance problem. I'm the good guy, I go and fetch a debris which is not mine. I have a collision while going down. Who's liable? Am I? Is it me or debris? And even some political issues. The active debris removal are quite close to military activities. If I'm able to go and fetch one of my debris, I'm able to go and fetch one of non-mine, non-debris. Okay. So, last chart, the future. Unfortunately, the future is not that bright. Today we have a rather low compliance with mitigation rules. There is plenty of publication about it, for instance from Dr. Belado Perez here. We have globally a 50 to 60% compliance, out of which in reality 90% of those good guys are just compliant because they are in altitudes low enough. There's only very, very few of them which do really effectively do something. So we need definitely to improve this in the coming years. We're hopeful to have an increasing number of orbital launches throughout the years. What will be the model in the coming 50 years? And we have plenty of topics linked to new space, more and more private and commercial application. So what are the applicable rules for this? Increasing number of small, uncontrollable satellites. Well, CubeSats are wonderful. CubeSats are really so enjoyable. It's wonderful to imagine that any university now can make and build its own satellite. But be careful. If you leave it up there at a too high altitude, it will remain forever. And of course, for those who have followed this week, there's plenty of questions about mega constellation satellites. Space World Foundation has predicted or forecast that there could be plus 9,000 satellites in the coming 10 years. So, well, what do we do with them? So the future is quite fuzzy and potentially critical.
Thank you very much, Christophe. We're going to hold on with the questions. You will see a few more presentations about space debris, and then you can ask questions. Okay, so now we have Dr. Francesco Toputo, who's going to show you something of what we have done within Stardust about space debris.
Thank you, Max. Good morning. I'm Francesco Toputo I'm an assistant professor at Politecnico di Milano and also a co-founder of Dinamica, an SME, which is a beneficiary partner of the network. So I was invited here to show you our solutions from the engineering point of view for what concern of what we have done within Stardust. Because of time constraint, I focused on only one exercise, one case, but I can assure you that we have done much more than what I'm going to talk about. So beside being a research network, Stardust is also a training network. So we are funded by EU to train 15 people, and in general to train next generation of engineers to tackle this kind of problems about space debris and asteroids, because they are emerging problems, and it's likely that they are not studied in the classical institutions now. So what we did, we wanted to train these people, and we wanted them to practice themselves with a big exercise of a series of exercises. And on top of that, we wanted also to train the researchers on how a research proposal was to be written, because, as you know, now the competition is such that if you are not able to write a very good proposal, although you have a nice idea, you can't get the project that you want. So we issued an internal call among the researchers. This was a couple of years ago, and all of them had together into consortia. It was a very good exercise, actually, and we evaluated their proposal, and this one was awarded, and was carried out by 4 of our researchers: Kartik Kumar from the left to the right, Kartik Kumar, Marko Jankovic, Natalia Ortiz, and Juan Martin Romero, and they are from 4 different institutions. So it was an internal working group, interdisciplinary, and also that involved 4 different partners within Stardust. So the idea and their proposed that was implemented was to do a big exercise of preliminary design of a space mission to remove a large rocket body. As you can see on the left here, those are the number of objects in MEO and GTO, and there are many Ariane rocket bodies. These are big, of 5-meter diameter, and they are in GTOs. 117 are in GTOs, and they have multiple passages in the protected region. They are big, so they are a threat, and therefore the idea was to design a mission to demonstrate that these rocket bodies can be removed by using an active detumbling strategy and a robotic manipulator with a sum cost cap of 200 million euros. And here on the left-hand side, you can see the solutions. The solution the researchers came out with, and the goals of the exercise. So this is their solution. All of the details, of course, again by lack of time, are given in this paper, which was presented last year at IAC in Jerusalem. But the key idea was to study the mission concept, and the 2 main topics were the detumbling device, which was a contactless device based on eddy currents, which was developed at the University of Southampton by Natalia Ortiz and their supervisors, and which also validated experimentally at Airbus Defence and Space, which is, by the way, an associate partner of the network, and a semi-rigid clamp plus a robotic manipulator to insert a deorbiting kit in the nozzle of the Ariane rocket bodies. Here you can see also the GNC part, and also the mass breakdown they came out with. Of course, details maybe we don't have time to go into the details of all of these, but the idea in these few minutes was to show that these exercises have been done in Stardust. There are also other engineering solutions that we have studied, and that the researchers are really putting their hands on in the 2 problems, which are space debris and asteroids, which are the problems typical of the network. Thank you.
Thank you very much. So we can now move to the next presentation, which is again about space debris, but a different problem. There is more the tracking and the orbit determination related to these objects. Okay, they are not as easy to track, and the orbit is not easy to determine accurately enough.
Thank you, Max. So, ladies and gentlemen, queridos amigos, it's a pleasure to me to be here and to introduce some issues concerning the challenges that we have today on space debris surveillance and cataloging. So, which is the problem that we want to solve? And first of all, what is this? So this is a series of images that have been taken by an optical telescope of the Geo region. So this optical telescope is a part of a space surveillance system which is composed of radars, telescopes, used on surveillance mode, on tracking mode, on both. And from all those sensors, we're going to obtain data that comes from regions where we have clusters, we have constellations, data of isolated objects, misdetections, false alarms, and from all those data, what we want to do is to know what's going on up there, catalog the objects, and use this catalog to collision avoidance, to re-entry, and to other activities. Okay, so what to do that in a right way? So with this short introduction, what I wanted to say is that surveying the space is not about taking a look to the sky, but it's about taking a look in a smart way. Okay, so first of all, what do we have here? Here is the distribution of geo objects when we propagate them over 1 day. So we see here we have it's radial section declination. Here we have the control objects, and here we have all the space debris and non-control objects. On this figure, which is from the Astronautical Institute of Bern, we have our observations, tracklets, from which we were able to compute an orbit, an initial orbit. We see here the mean motion and eccentricity. So red dots are observations, and blue dots are those observations, those orbits that could be correlated and included in the catalog. So what we see here, we have the geo objects, the GTO, and we see a lot of red points, which means that we are observing a lot of things that we are not able to include in the catalog. So which are the main challenges to be able to improve that and to have a better knowledge about what's going on? The first challenge is how to define observation strategies. So what we want to have leak-free strategies. We want to observe the sky in a smart way. So we are going to have task observation, survey observation, and both. Then we have a question about multi-sensor data fusion. We have a lot of sensors, and we want to use them in an optimal way. So how to fuse all that data, how to correlate all that data in order to be able to include those objects in the catalog. Then we have the catalog build-up and maintenance. This is how can we able to build up in an efficient way and maintain a catalog. So we have consideration on covariance, on errors, covariance propagation, covariance-based correlation, problem with high area to mass ratio objects and with maneuver objects, which are a lot of those red guys here. We want to get those red guys in the catalog. And the last challenge, one of the other challenges are, of course, the characterization of attitude and orbit coupling. We have those red guys have an important coupling between attitude and orbit. If we are not able to characterize that, we will not be able to include them in the catalog. So thank you, and we will discuss later on.
Thank you very much. Thank you. So you can see a lot of challenges, and in Stardust we had a mix of engineers, mathematicians, physicists, so each one also provided a different solution, and what you're going to see now from Professor Gronke is one solution that comes from math to this problem of orbit determination and track.
Okay, thank you. So
within the Stardust network at the University of Pisa, we searched for new methods for initial orbit determination, where the orbits are computed through correlation of very short arcs of observations. Indeed, we worked both with optical and with radar observations. But today I will briefly speak what we have done with optical observation, that is angles-only observations. Okay. So we use very short arcs. What are very short arcs? Are small sets of observations like rate ascension and declination taken in a short time interval. So from these very short arcs, we can compute what is called in the literature an attributable, that is a vector of angles, alpha and delta, and angular rates, alpha dot and delta dot, and these taken at the mean epoch of the observation. So you see that here we have 4 quantities. What we miss to have an orbit is just the range and the range rate. So our purpose is just to find a way to compute those quantities. So what we did is to try to use the first integrals of the Kepler motion to correlate 2 VSAs, 2 very short arcs of observation, and compute initial orbits. In particular, we can equate the angular momentum or the Laplace length vector or the energy at the 2 epochs of the 2 VSAs that we are considering. Which are the advantages of this formulation? First advantage is that we can write the equation into a polynomial form, and this allows to compute all the solutions at the same time. Another advantage is that using conservation laws, we can try to link together, to correlate VSAs that have been taken after multiple revolutions. This is also a big advantage, mostly thinking about space debris. Indeed, these methods that we are developing can work both for asteroids and space debris. And this point of view, this way of thinking, started very far, in 1977, as soon as these observations were available. And in a paper of Tuff and Hall, the conservation laws, angular momentum and energy were used, but they didn't use the polynomial form, and so they encounter some problems, and the results were not satisfactory enough. More recently, we have taken this technique, and with different combination of these integrals, we were able to find polynomial equations of different degree. For example, in 2010, we succeeded in obtaining polynomial equation of degree 48, which is quite high in the degree indeed. But 1 year later, we decreased the degree by using a different combination to 20. And within the Stardust network, in 2015, we were able to reach a degree 9. So the question is it worth to try to continue the research in this sense? That is this, can we do better? Indeed, we can prove by some mathematical tools, Graebner basis, the name that doesn't matter, this is a theory concerning multivariate polynomial, that this 9 is just the optimal value. So, another achievement of the Stardust network is a new method, initial orbit determination, to correlate 3 very short arcs of observation. This can be done also with the Keplerian integrals, what we use in this case is the angular momentum only. We obtain in this case a polynomial of degree 8. Here I conclude by showing an example of application of these 2 methods to the initial orbit determination of asteroids 2014 YW11 using the Pan-STARRS 1 optical observation, which are very good indeed. And you can see the 3 attributables that we consider. One is centered February 2012, another in December 2014 and in January 2015. So here in the last table, we display an initial orbit computed with the correlation, with the method that correlates to VSA. In the second row, the 3 VSA's correlation, and you compare these results with the least square solutions. So that's it. These are the main references where we have written explicitly this method. Thank you.
Thank you. Thank you very much. So before we go into the future of space debris with the University of Arizona, let me give you an overview of other techniques that we developed within Stardust. One thing that we look at was very exotic disposal maneuvers, for example, for the satellites that are orbiting the libration points. And in this case, you have so many nonlinearities that you cannot use the covariance matrix, which is a standard technique that is used in uncertainty propagation in celestial mechanics, because the covariance matrix would give you this sort of dispersion of all possible trajectories, virtual trajectories, but instead the correct one has a much different shape. And if we are trying to dispose of these satellites, making them impact with the moon, you would basically miss the moon. We developed techniques to be able to propagate this uncertainty, both in the case in which you can have access to the simulation code, because maybe you wrote it, but also in the case in which a company is providing this and you cannot have access to this code, but still you want to be able to do an uncertainty analysis very fast without going for a full Monte Carlo simulation. And we apply this to collision avoidance maneuvers, in which you have to maybe correlate the motion of 2 spacecraft, and that needs to have very fast computation, but also to the re-entry of these objects. And so we needed to have very fast techniques to be able to calculate the probability of having an object hitting the ground and causing damage. So we imported some techniques from computer graphics, for example, and that speed up immensely the calculation of the whole re-entry trajectory and allows you to calculate the probability of a particular object falling on your head. Now that you've seen an overview of what we have done, we can see what can be done in the future with Professor Roberto Furfaro from the University of Arizona.
Yes, thank you very much. Just to give you a little bit of a background, I'm an associate professor at University of Arizona. I also direct the Space Systems Engineering Lab. I'm part of OSIRIS-REx at the Science Processing Operations Center. But what I'd like to do also to bridge, give you a little bit of glimpse of the activities that we've been doing at the University of Arizona. We're very much projected forward. Actually, our university heavily invested in space situation awareness because we convinced the provost, actually, we wrote a proposal to do a cluster hiring where we recently hired 5 professors who just work specifically on this problem, and it's quite a bit of significant investment from our department, from our university provost. So what happened is that one of our major acquisition, actually in this past 6 months, was Dr. Moriba Jha, who established an initiative which we now call Space Object Behavioral Science Initiative. And I give you, of course I don't have the time to go into details, but I want to give you a little bit of a glimpse of what we are about. So we look at racing and space objects, and we want to understand the behavior, right? And we have quite a bit of data that nowadays, with a lot of sensors, distributed all over the nations, we can collect. And our question is that how can we characterize behavior? And the holy grail, of course, of if you know behavior, you also can support a decision about, what racing objects are. Are they controlled, uncontrolled? They are adversary, or what are the intentions, and so on. Also another consideration we had when we started this initiative is that we are are in the era of big data analytics. Analytics is one of the buzzwords. It's a little bit less scientific. It's open to different interpretation. But what we are about is to infuse quite a bit of the techniques from machine learning and artificial intelligence into analysis of data and into characterizing behavior. Indeed, one of the questions that I started looking at, personally, and of course most of the team, is what does behavior mean? To us, behavior is clustering. If you have a bunch of data and you do a clustering analysis, which is typically an unsupervised methodology that you can take from artificial intelligence, you can look at systems of objects that behave the same way to cluster in groups, right? And actually, if you do an analysis, a deep analysis, you can also find out subclusters, which help you identify how different behaviors subject to different characteristic physicals, right, and a different kind of also physical, physical response, can nevertheless behave at the same way. So one of the things that we've been doing is start looking at, supervised, unsupervised machine learning methods for data analysis, for example, to go from raw data to mapping physical features like angular momentums, angular energy, things like that, then do cluster analysis that can eventually inform also networks for classifications. In this case, we're pretty much very fast forward into the concept of deep learning, which is one of the most powerful technique that is, has been recently developed. But also, and then I want to talk about this with the next slide, developing this concept of ontologies coupled with Bayesian network to support decision, okay, interactively and do intelligent reasoning over data. Okay, so for example, recently we wrote a proposal to DARPA where we proposed them to, get us funding to work on developing knowledge base for decision making for resident space objects, and ontologies are at the key, at the core of our approach, because ontologies are methods where you can capture knowledge base, that is, what do you know about your space objects, and do association between different concepts. And most importantly, they're shareable and reusable. So you can build a large, database that you can reuse and share with different type of system. In this case, for example, we look at the problem of as a case study of IACD compliance for a graveyard orbit, right? If you have how do you know, for example, that a certain object is compliance, once you dispose at the end of life? And we try to look at the problem of fusing hard data, which I'm talking about measurements like determination and other, other inference that comes from data with soft data. For example, natural language processing, where we can process information from the data because somebody puts out there an information about an object so we can correlate with the measurements. And therefore fuse the information in the Bayesian network, which is based on the ontology, what we call SOBO, Space Object Behavioral Ontology Bayesian Network Belief. And that's about it.
Thank you very much.
Thank you.
Thank you. Okay, so now we have a couple of minutes if you want to ask a question to our speakers. And meanwhile, I show you this slide. Nope. Okay. Can you put the presentation back? So if you want to know more, go on our website and Twitter account.
Yeah, quick question. For these more immediate solutions to orbital debris removal, are you guys going to do ride sharing, or are you guys going to buy out the whole rocket to put a payload on to do orbital debris removal?
Can you repeat, please?
What? Say again?
Can you repeat?
Are you guys going to do, for your orbital debris removal missions, are you going to go ride share on another rocket with your payloads, or are you going to buy out a whole rocket to put a payload on?
Well, actually, this is not yet analyzed. I mean, the launch was not an option in the exercise that we did, if you're referring to the presentation that I gave. I don't see who is.
Other questions? There is a microphone. If you can pass the microphone to the lady there.
Hi, my name is Anastasia, and I do space debris. I'm like trying to build a startup about this. So the main question I always get from investors is, where do you get the funding?
Well, one source is the European Commission, very generous funder. The other one is ESA. Of course, the type of funding is different, allows you to do different things. The European Commission is more bottom-up, which means that you can invent new things and using your imagination. But also national agencies, CNES, DLR, they have funding as well to support projects and initiatives. The UK Space Agency, some.
So when can we expect you to be in experimental phase, like building things and testing things?
At the moment, there is no plan to build anything, so I cannot give you a date.
If you allow me, I'd like to be a little bit more precise for a startup. You're talking about the operational phase. Where does money come from? And then you can have two kind of business model. First of all, the satellites, for instance, from mega constellations, which are stranded up there. For instance, I don't quote any name, but a constellation going to 1,200 kilometers with 700 satellites. If they are stuck up there, it's for 2,000 or 4,000 years. So definitely they'll be ready to pay to have someone going and fetching them. So that's a business model. Second point, you know that you have small collisions destroying some active satellites. So this is linked directly to the number of debris regeneration. So if you retrieve some large debris, you will diminish the probability of collision. So somewhere there's a business case to be made. If I invent anything, if I retrieve 25 large debris, I save 1% probability of killing 100 satellites. See, so maybe there is a business here. So we're working, there are 3 or 4 different ways which are considered like this for financing the activity in the operational regime.
Okay, thank you very much. I think we are at the end of this session. So if you have more questions, our panelists will be around still for a few hours, probably not all of them, because we have to go to the airport. Thank you very much.